Good morning or good afternoon, guys. How are you? Hello. Can the comrades hear me?
Yes, sir.
Yes,
Wonderful. If the comrades can hear me, which means they can also see my screen. All right, guys. Today we're gonna look at the notes that I posted online. Those notes that I posted online are very, very important. They sustain your knowledge. So if there's some stuff that in class maybe wasn't discussed according to your understanding that you like, you can go there, look at them, and then add more to understand your work. Right. So today we're gonna start from what page 26. That's where there's what is called design activities. Right. I want us to talk about design activities. I wonder where the other comrades are. These are the last topics. Usually these last topics are the ones which come on major tests or exams. And then tomorrow when you don't understand, you start blaming the ancestors or the God and say, I God has forsaken me. Why the ancestors have forsaken me? What is your own doing? Let's give them a message. Avoid absconding. Last lectures. So, all right, guys. I want us to talk about design activities. All right. So everyone at a certain point or at a certain stage in their life, you all know or have heard about what design is. For example, people who watch House of Zwidi, you always know that Zwidi there designs clothes. And for some people who like electronics, like the guy I was talking to during the holidays, you understand that there's always a design that you need to do that can help us as humans out there. Right now, I'm even trying to do a design in the park. You know, the park that I gave you yesterday is a design that is happening, which is already there in your houses. Have you seen that nowadays, the houses, not counting these light bulbs which can be charged, there are houses with lights outside. You find out there's no one in the house, but at a certain point, the light turns on. At first, you think, no, maybe this light is programmed that at 5 o'clock or 6 o'clock it turns on. But you find that, no, man. This light, if it's cloudy on a certain day and it's not yet 6 o'clock, the light has turned on. How come? So that was the light-dependent resistor that we were talking about yesterday. So one of its uses is in the homes. When you know that you are busy, you forget stuff like that, and you don't want to waste electricity, you install it on your house, right, on the outside, and connect it to the wiring of all the outside light bulbs. When it's morning, the sun comes out, or light intensity is now increasing, it will just switch off the light bulbs. When it becomes dark, it will just turn on the circuit and turn on the lights. You see, so everything we do is an application on the outside. So I know some people yesterday, they were just listening and they're like, Minera, why sometimes are we learning these things? This thing is useless. No, these are some of the things that when you go to your learners now, you're explaining to your grade 7s or 8 or 9, they're like, look, young man, this thing is there in that house at the corner there by our school. Do you realize that at this hour the light turns off, at this hour the light turns on? Sometimes when it's cloudy, raining or what, the lights turn on. The young men will be enthusiastic about what you're teaching because they are seeing the applications out there. You now go on and say, have you ever heard of daytime running lights in a car? That's a light dependent resistor now, but with a positive coefficient. It's the opposite of one that we know. This one, when the light is on, its resistance is gone. It turns on the lights. When it's dark, then other way around. That's daylight running lights on a car. You explain to these kids, they get excited, and the more they come to your lectures, your classes and stuff, and the more they pass your subject course, whatever it will be called at that particular point. So whatever we've been discussing here and those components that I was showing you in class on the other day, on the other lecture, they are very important because you get to use them, get to apply them. For example, I can maybe try go back and show people, sometimes it's nice to show people what we've covered again so that you kind of repeat and they see things for what they are and stuff like that. On the section of electronic components, right? These are the things that we went through. Going too far. I don't want us to spend too much time on things we covered. So this was the section that we did about electronics and components, right? There's a point where we discussed what integrated circuits are. And then we discussed about integrated circuits when I was showing you what an IC. I remember in class I was saying you would hear those funny mechanics, those people who repair TVs and what say, it is blown an IC. And they will be talking as if it's the most sophisticated component in the entire world, yet it's something which costs 7 rand at Mantech or DIY electronics. And then they're gonna charge your parents something like 1,000 rand to fix that thing. Yet you can solder with your own hands. If you only you knew what it was that was dead or broken in the TV or radio, you wouldn't have paid all those lots of money. So it's unfortunate that some of the things we learn at school we take for granted. For example, I was even talking about magnetism the other day in the other lecture. There's a series on Netflix. It's called Breathe. I can't remember. It's either it's Breathe or Survive. The girl had to use basic things that we learn in class to magnetize a pin or a needle so that she can make that thing a magnetic compass and use it against the magnetic field of the earth to determine when north and south is. So you see, even the movies, they give you these ideas. Yesterday, we were talking about another basic knowledge that we did in class. You've seen it in Fast and Furious movies where they make an electromagnet and they put it in use. So we just watch sometimes movies and we don't think this thing, we learned it, we did this thing. Basic application. So design is one of those things. Get to apply the knowledge that we did here to make your classes interesting for your grade 7s and 9s there. You see, when you're talking about things that they see and you're spicing it up there, they get to enjoy what you're doing. So we once talked about resistors, right? And then I remember I was talking about also capacitors, that they are also non-ceramic and polarized, things like that. This is an example of a special resistor. I remember we talked about ohms. And then this was, I think, one of the things which was confusing people. I think they never got to understand how this thing works. But hence I posted these notes. I thought people were gonna actually go online, look at the compensatory notes that I uploaded and check what we did in class against these compensatory notes to see and understand. So I noticed that some people didn't know how to answer such questions. They relied on Google. Since I was not there on the test and it was online, some thought they are smart. They will just go on Google if the color is what, or say resistor calculator on Google and then punch in the colors and then voila, it gives them the answer. So you have to know these things. You see, the first bond denotes the tens, the second bond denotes the units, right? So, and then and so on and so on. Black is 0, brown is 1, red is what, and then the other one is a multiplier, you see. So that gets to give you, for example, this one you can see here that the first color is yellow. That means you have a 4 there, right? And then you come to the second band. The second band is something like purplish. Is it violet? That's violet. So you have 47, right? So we're done with first and second. Now you come to the multiplier now, the third band, right? Of which the third band here is what is red. That means by 100 there, that's what you're multiplying with. And then we come to the final band, which is tolerance, right? Which is tolerance there, of which tolerance we didn't put, but it's usually plus or minus 1, plus or minus 0.01. of which you can see this one is silver or white. That's what? Plus or minus 0.01. So which means here it's something like 4,700 ohms plus or minus 0.01, the resistance of this resistor, right? So in which it's usually written as 4.7 kilo ohms plus or minus 0.01. Hence you've read the value of this resistance. But I saw that people didn't understand what's happening. And then, for example, now, if you have, let's say they give you the vice versa now, they say find the color coding of 5.6 kilo ohms, right? With plus or minus of 0.1. They want the color coding of the resistor now, you see. So now you have to check 5.6 kilo ohms, which means this is 5,600, right? Ohms, right? So you can already tell that, okay, the multiplier is 100. So it is supposed to be a by 100 here, right? And then you check now, if it's by 100, what is the first band that I should have? What is representing 5? That's green, right? On the second band, what is representing 6? Right, you can check that's blue, right? And then on the third one, what is representing the multiplier 100? That's red, right? And then you come to the tolerance, the last band, it's 0.1. That's represented by gold. So which means your resistor was supposed to be something like this. It's color coding. First band, we say it is green, right? So you will have green like this on the band, right? And then the second color, we say it's supposed to be blue. And then you're gonna have a second band of blue there. And then the third color of the multiplier, we say it is red. Then you're gonna have red there, right? And then the fourth color now, which is the tolerance, it's gold, right? And then I don't have gold here, so I'm gonna use yellow. So you see, now we've done the reverse with 5.6 kilo ohms plus or minus 0.1. The resistor looks like this, right? You went reverse away. We're given the colors now, wanted to find the value. We did find the value, right? So this is a simple thing. That I realized that people don't know how to do it. They were guessing. So take note, guys. These notes are not there for decoration or just to waste space on Learn 2022. They are for you to compensate your knowledge that we did in class. Learning doesn't end. No matter how much someone can explain something for you or to you, you will still have to go on to other sources on your own so that you can clearly understand something. Now, the other thing that I saw, potential dividers. This one is about, I saw that people don't understand what a potential divider is. A potential divider is when, for example, you're given these two resistors, right? You want to find, you're given a voltage, there will be a V++ there, and then maybe it's either 0 volts here or minus V++ or ground, whatever you call it down there, right? So now, here now, I want to zoom in this thing so that it can be visible. So now, if you want to find out what voltage is charged by the resistor here and what voltage is charged by the divider, dividing, right? There's a potential divider on its own, which is a variable resistor. And then another one, which you call a potentiometer, which you use with a screw. But if you're doing it manually like this, you first have to calculate your total resistance, RT, right? These ones are in series, which means that's R1 plus R2. Then if you want to find out what voltage is charged by this resistor there, R1, you're just going to say R1 over R1 plus R2 multiplied by the V in, which is there, right? You'll get the voltage across R1. If you want to check this one against R2, you're going to have R2 over R1 plus R2, right? Then multiplying by V in. Then you get your voltage there. Or vice versa, if you go to the one that is charged by R1, you can now just say V in minus V R1. You will get the rest, the remaining one for R2 from KVL, Kirchhoff's voltage law that we talked about. So that was one of the things that I saw that people are just doing, but the understanding is somehow something else. And then this one we talked about, it's something that you're gonna be using in the prac, the LDR, so we've been talking about even now, of which these are examples of capacitors in real life, how they look like, right? So when you see these capacitors, why is it doing this thing? Right, I want you to do this. I want it here. So this type, this is the ceramic type, right? These are the ceramic capacitors. This kind, the blue and it's orange. I'm colorblind, so. And then this one here, that's the polarized, right? Polarized capacitor. It has a plus and a minus legs. The positive is usually longer, and then the negative is usually shorter. That's when you determine that this is the positive leg, this is the negative leg. Right? You see by the length of its pins. These ones, ceramic, they are non-polarized. Non-polarized, you just plug and play, yash, just like that. You see, these are the polarized one that we're talking about. A non-polarized one are usually what? Ceramic. And then we talked about the diode. You remember that a diode in class, we represented it like this, right? That's how we represented the diode, right? Where the other side is the N-type, the other side is the P-type, according to semiconductor theory. So a diode looks like that when you're drawing with your hand, but physically, in real life, this is how a diode looks like, right? It is polarized common with two leads called the cathode and the anode. I remember we're talking about that. The cathode is normally marked with a silver or colored band. So, which means that's the cathode to this side. This is the anode on the other side, right? And then this is how we represented diodes in a circuit, right? Where I remember we're talking that current will only flow in one direction, which is pointed by the diode. For instance, here, this is forward bias. I remember we talked about that in class. When it's like this is a reverse bias. You can see that the positive is facing this way, but the diode is opposite the flow of current. Hence, we say it's what? Reverse biased, right? And then this is the light emitting diode, what we're talking about, that people are going to see in the prac. This is how it looks like, right? This is a light emitting diode, right? This is how it looks like. It has two legs, and then as usually, this will be like this when you see it in, and when you're touching it in real life, it will have two legs like this. The longer one is the positive leg, the shorter one is the one that goes on the negative terminal. So if you have a battery of 9 volts, the longer one goes to the 9 volts positive terminal of the battery, and then this one goes to ground or the negative terminal of the battery. And then this is a 7-segment display. You remember we once talked about the 7-segment display, and people were wondering, why is it called a 7-segment? I replied and said, because of this, right? It's like this, 7 segments. That's 1, 2, 3, 4, 5, 6, 7 segments. It uses those two to write up or to show up a screen. When it displays ones, it just uses 2 segments. Just as you can see, 1 is 2 segments there. And then and so on for 2, it uses 1, 2, 3, 4, 5 segments. Right, you can see that. And then for 8, it uses all 7 segments. That would be 1, 2, 3, 4, 5, 6, 7 segments. That's for writing 8. Right, so that's a 7-segment display. But now, if you find it writing nicely now like this, with now drawing nice clouds, that's no longer a 7-segment. A second segment is only horizontal, vertical lines that it uses, right? So this is semi 7-segment. It's part 7-segment on top, and then on the other part is just like the multi-crystal displays that we know of cell phones, TVs, etc. And then our batteries, everyone knows. AAA size is the remote size that we know. Even the AA, some older remotes which still take bigger batteries, right? Then the C type, you know, is big, D is big, and then PP3. That's car remotes. I'm sure you know it. That small one which goes into a car remote or a watch or something like that. And then these are the symbols that you guys have to learn on your own. How a cell, this is a battery is represented, how a light emitting diode, blah, 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 and all these things. So now we come to the main event of the day. I wanted us to talk about design activities. But everyone knows that at a certain point, we have to design. But before I start, the comrades are fine so far. I hope and I hope that the comrades are still following. The comrades are still following, right? They are not lost.
Yes, we're still following.
All right. So now,
So,
yeah,
sorry, I just wanted to confirm. You said that you posted this on Learn already, this document.
a long time ago. Just look under, you see topic 0 where there's the course outline and the class links for logging into Zoom. The document is there, somewhere there at the top.
Oh, okay. I didn't know that. Thank you.
All right. So now, this one about design activities, guys, you need to know the steps of design. Where do you start? What approach do you use for designing things, right? So when you're designing things, right, there's also what is called, before we get into the specifics, there's also what is called a top-down approach. In my entire life, I was shouted over this by my own supervisor. There's what is called a top-down approach. Right. This one means that you'll be given or you'll be thinking of a bigger picture, something that you need to design. So it's called the top-down, right? This top-down approach. It's an upside pyramid, top-down approach. Right. So what happens is, it's like, I will explain it the way that I was shouted it and how it was explained to me. They said that you are in Edu. In Edu, you are aware in the technology and what class, right? But before there's the whole world, right? It's the whole world. That's the bigger top. From the whole world, you have the African continent, right? That's the smaller top. From the African continent, you have Southern Africa. That's another smaller bottom. And then from there, there's South Africa, there. There's Durban, there, right? And then finally, there's campuses, you down there in Pinetown, Edu. You see that? So you have a bigger problem, but you keep hammering it, going down. First, you tell us what's happening in the world, what people have done, what they're still doing, what you intend to do, and then you keep going until you hit the nail home on your own point. So that's how design is done. For example, let's say you want to design a smart TV that doesn't use electricity. Somebody has already designed a TV that doesn't need batteries or electricity already. That TV only uses waves in the air. It's there. If you have time, after the lecture is done, you can Google it, TV that doesn't use electricity or batteries, you'll find it. So what you do is, you have a bigger thing. You want to design a TV, but the TV is split into many parts, right? There is the power supply part, there is the screen, which is the 7-segment display or natural display that you know, right? And then there is the part where people must, the interface, pressing on, off, increase volume, change channel, etc. Right. So you're gonna split these things into 3. You see, that's your top-down approach. You have the bigger problem. Now you have split it into 3. And then those 3 things, you're gonna split them again individually on their own into smaller pieces, such that at the end of the day, you start with the smaller end. You fix it, it works. You go on to the next step. You fix it, it works. You keep expanding, interconnecting your things until you have your upside pyramid, right? So that's why it's called the top-down approach. You must know, and when somebody asks you a question, what is your design style? What is your approach? You just tell them, I'm using the top-down approach. And then when they say, what do you mean by that? You just give them an example of an upside-down pyramid. They ask you, even life problems. Someone asks you in an interview whatsoever, like I attack life in a top-down approach. Bigger problem, split into smaller things that I can manage, and then I build them piece by piece, compiling them. If it doesn't work, I wait until I solve it. Then I compile it with the others, becomes bigger and bigger and bigger. And finally, you have your entire big pyramid. And then it's done. So now on design activities, there's what is called, when they say the development of a product starts with the design brief. That's what you are given, a design brief. Designing what. Or for example, the project that I gave you, I was like, design a device that when ESCOM goes, this happen, or vice versa, when ESCOM comes, this happen. That's a design proof, right? Specification is the statement that tells the designer exactly what the product has to do. So when you have your brief statement, you come to the specifications. On specifications, there's what is called functional specs and what is called non-functional specs. On functional specs is the things that the design must really do. For example, what does the TV do? We have to watch just to show pictures, a movie, things like that. Non-functional is things like artistics. It must be black, blue, it must be nice looking, it must be robust. That means if it falls or water comes, it doesn't enter. Those are non-functional specifications. Things like artistics, robustness. But functional is what it's supposed to do, the real thing that it does. And then from there, you go in and evaluate and test what you have done throughout the process to make sure that the quality standards are being achieved and to improve, to identify improvements, blah, blah, blah. So designing electrical components, sorry, it's zoomed here. I'm trying to unzoom it. I can see there are two texts here. Let's see. Oh, she didn't know that they uploaded a long time ago. So now, designing electronic products, the products are developed to meet and meet. That's what you want it to do. The designer is given a design brief, which outlines what the problem is. We've talked about this. System diagrams. Now, you must be able to represent your design or your system. There's what is called a high-level functional block diagram. That high-level functional block diagram is a diagram which describes the blocks and pieces of your design. But that one is too much for you guys. You need to put it in a simple way. Input, what does the design want? What do I put in? And then you must know the output, what should come out, and then you must know the process. For example, they gave you there an example of a vending machine. At the end of the day, what are you looking for? You're looking for a drink or you're looking for chocolate bars. That's your output, right? On the vending machines that are out there in the world. They used to be there on campuses, but just because the comrades, when they don't get what they want, we tend to demonstrate. So we killed all the vending machines on campus. But otherwise, if they were still there, your output would be chocolate, chips, drinks, etc., water. That would be your output. But your input will be you putting coins, your money, right? But the process, the machine there, what does it do? It's a coin counter. You see that? It's a coin counter. And then this comes back to another example. Check out the mall, right? When you enter a mall, there's what is it called? A bar. I've forgotten the proper name. A bar lift. When your car comes in, right, you have to wave your hand there. That's your input to signal that your car is in front of the gate. And then they give you a ticket. That would be your input. And then the process there is the camera shooting your number plate in your car. And then the output, you want to enter when you want the gate to open. Vice versa, when you come out. When you come out, your output is you want the bar to open. What is your input? Your input is your ticket that you paid for. The process is what is it? The process is the camera now and the computer there, checking your number plate of the car and the ticket. That does the ticket on the number plate represent the ticket or the number plate on the car. If they match, then it checks again, is it paid? Yes. And then the bar opens and then you go out. So whatever you design, whatever your system is, you must know your output and your input. The process is simple. What's important to know is what exactly do you want to come out and what exactly do you intend to put in. This inside is simple to do. So this is what is called signal flow diagrams or flow chart diagrams. So when you come across a test or whatsoever, they say, give a flow chart or signal flow diagram of a hair dryer. You must know that they want this. They want you to say, for example, here is a hair dryer, right? The ones that the ladies use a lot, right? What is it at the end of the day that you want to do to get your output? So an output, you want hot air or dried hair. That's what you want. You want your hair to be dry. Hot air coming out or dried hair. Input, what is it that you're putting in? You're putting in electricity, electrical energy, right? Your input is electricity or you call it electrical energy, right? Then the process, what is it that's happening? There is a conversion of electrical energy into heat energy and kinetic energy. So inside there, you're converting your electricity into what? Into heat energy, which will then push the hot air inside there, and then there is a combination of heat energy and kinetic energy going out. So simple. What is your output? Hot air or dried air? What is your input? Electricity or electrical energy. Process inside conversion of energy. Simple. That's that. You go again, you use another example. For example, your stove at home. Electrical stove or heat gas stove. We can start with the electrical one. What is your output? You want heat from the stove. Don't say you want cooked food because that's not what the stove does. You are the cook. The stove only gives you heat energy. That's the only thing you need from the stove, heat energy. Right? What do you put in there? Electricity. Process conversion of energy. Right? So be careful when now you're answering these things. Because somebody here will come and tell us cooked food. The stove doesn't cook. You are the cook. We're talking about the device, not your functions. What do you want out of the device? Heat energy. What do you put? You give it electricity. What processes are happening inside? Conversion of energy. All right. So these are the examples that I can give you. So you must be careful about this. And someone can come to you and say, for example, a car. They can give you a car. What is it that you want? The output of the car. You want what? Motion, movement. You want motion. You want it to go, move. Right. But what do you feed it? Fuel. It's either petrol or diesel or gas or electricity. Right. And then the process, what happens is the conversion of the fuel into kinetic energy. That's conversion of energy. Done. Simple as that. And then you will hear somebody saying output, I want to arrive in Joburg. You are the one who drives to go to Joburg. The car only gives you motion. You are the one who now directs it and then stops it, breaks it, whatsoever, and make it arrive in Jos, wherever you are going. But the only thing that's the output is motion. So don't go out there writing unnecessary stories here on output or input. You'll find some people here now writing a composition. No ways. Don't do that. There's another question there on the chat. Oh, yes. Thank you, Busisi. What is it called? A boom gate. Yeah, it's a boom gate. You're right. Now, there's what is called subsystems, guys. For example, now, what they are trying to talk about now, they're trying to talk about open and closed loop systems, right? Open and closed loop systems. So that what we are talking about here, when they're saying open and closed loop systems, is like this. First, we have an input, then we have a process, then we have an output, right? From input, we go to processing. From processing, then we go to the output, getting that. So you see this is called an open loop system. In layman terms, this is the open loop, right? There is no interconnection of the output to the input, no. And then what is called the closed loop system now? Closed loop. That's when now you have your input, you have your process, you have your output. That like that, that like that, that like that. There goes there, this goes there's your. But then the output comes back to the input, right? So for example, now we're talking about the stove, right? The stove is simple. You just feed in electricity, turn on the button, conversion of energy. The output is heat. It will keep on heating non-stop unless and until you switch it off. So that's an open loop system, right? You check again a blower. It only depends on your finger on that button that you're pressing. You plug in electricity, you turn on it, wire. It will keep blowing. You'll even get blown on your head or get hurt. It won't stop as long as you keep pressing that thing. That's an open loop system. But now let's look at a fridge or a boom gate. Let's look at a fridge. The fridge, you're gonna give it electricity, right, as your input. Then the process is there. It will fight to take out the heat which is inside and make sure that all the heat is transferred to the outside environment. That's why when you touch a fridge, you find that it's hot on the outside, but inside it's cold. So there will be that process. But the output now that you want is coldness, right? But however, if you bring something hot pap or hot rice or a hot pot and put it inside the fridge, it will fight inside to make that pap cold. That's what we call a closed loop system. It keeps checking its temperature or its coldness. If somehow there's something which is trying to disturb its coldness, it works against that thing. So this is a closed loop system which keeps checking what's happening to itself. It keeps correcting itself. If you set it on 3, that thermostat inside the fridge, it will make sure that it maintains that coldness on 3. If you push it to 1, it will decrease the coldness and make it hot a bit, but it will maintain that thing. If you try to disturb it, it will fight against the disturbance. That is what is called the closed loop system. It's self-aware. For example, the boom gate of a mall, right? So when you're going out now, what does it do? It will check first when you're coming in. It will shoot. It will look at your hand. It will detect your hand and then shoot a picture of your number plate. Once it does that, it will let you in and say, I go in. I am not worried about you for now. Process is now when you're trying to come out, you want it to open, but now here's what it's going to do. It's going to say, okay, is the ticket paid? Yes or no? Yes, okay, sharp. If no, it won't open. You have to go back. And then it will try again now. Ticket, is it paid? Yes. Is the number plate matching the car? Yes. They need to let you out. If not, you're going back until you satisfy it, right? So a closed loop system is a system that is aware. It keeps fighting against what you are trying to change on it. So you must be aware between a closed loop system and an open loop system. The comrades understand this. This is kind of weird. When now it comes a test, instead of giving you, we say, give us actually a thing that is like that, and then you will tell us. So someone is asking here, so say actually everything that is made, it's made out of these two systems, as in everything that is built or man-made. Yeah, it's like that. It's either it's an open loop system or it's a closed loop system. But there are some which are semi-closed loop systems. For example, to be specific and 100% on point, the boom gate that she was telling us about is a semi-automatic or semi-closed loop system, because it doesn't necessarily go back to input. It goes back to process. It denies you to go out only, right? But a fridge is straight closed loop system. It keeps fighting against the temperature. It's like an aircon. So an aircon, you know, an aircon in houses or wherever, right? If you set it on a temperature of 32 degrees, it will fight to keep that temperature at that level in that room or house or hall or wherever. It will keep fighting and fighting and fighting. You disturb it, you try to add more heat. If you add heat, it will try to fight using coolness. If you add coldness, it will change its thermostat there, starts using a heater to fight the coldness, right? So that's a closed loop system. It's self-aware, right? That's like, for example, something again that you can give as an example. You can check a car, right? You can check the petrol tank of a car. You drive it, it's self-aware that now I'm out of petrol, right? The moment it goes out, it shuts down, switches off, doesn't go anywhere. It keeps telling you, my guy, you're wasting petrol. It keeps telling you, you are now on 40, 30, 20. But this one depends on you pressing it. It doesn't fight alone. You feed it petrol every time it runs out. So it's semi-automatic, semi-closed loop. But if it's fully controlling itself, that's fully closed loop, automatic system. So you must understand the difference between these things: an open loop, a semi-closed loop, and then a fully automatic closed loop system. Now, we've done that. We've even talked about the thermostat. Now, giving us an example of a boiler pump and the radiator. We just did other examples which are almost similar. Now, there's what are softwares which are also called CAD software. This is computer aided design software, right? CAD. There's many of them. There's AutoCAD, there's MATLAB, there's C++, there's whatsoever. These other ones for 2D drawing, 3D drawing. There are so many softwares which are CAD softwares. And I understand that now in high schools, they provide computer workshops. There are now computer rooms, computer halls. They now provide these CAD workshops, technical graphics, etc. These kind of drawings. There's also softwares for making PCB. A PCB, I remember in class we once talked, is that board which when you open a TV or radio, where resistors and capacitors and transformers are soldered onto, where they are sticking, that board where they stick on, which is greenish in color and copper lines, that's a PCB. So there are softwares which do that. For example, a software which I know which does PCB design, there's one which is called Circuit Maker. There's other one which is called what's this one that I was using just now? I've forgotten its name. There's Circuit Maker, and then there's Multisim. It's called Multisim or Altisit. No, when you're saying motherboard, you're talking about a board of a computer, right? But that board of a computer is a PCB. So in other words, this thing is like that. It's called a PCB. And then this is the mother, the father and mother, the godfather of all. Motherboard comes from that. It's still a PCB motherboard. Whatever board which is component comes from the godfather, right? So when I was talking about CAD softwares, I was making you aware of the softwares that you use. For example, when we're going to the prac, right, you first do your circuit on a breadboard, right? You first use a breadboard like we talked yesterday. And then from breadboard, you test on a veroboard. This one is where you solder onto a board which can take high voltages. From veroboard, that's when you go to PCB. Your product is finished now. It's ready to be packaged for aesthetics. So breadboard, you're building and testing. Veroboard, now you're testing that after soldering the components, how do they sit, how do they look? From there, you put them on a PCB, which is designed now. You see, a PCB can be designed to fit a small box. A veroboard and a breadboard, you can't design it to fit a small box. This is your playground where you test on, your practice playground. But PCB now, you're the master. You're putting it in a small package that looks nice and is unbreakable, blah, blah, blah. A cell phone, for instance, how it's put inside. There's a motherboard inside the cell phone. You know that, all of you. But the smallness and the parts in there, that's the specialty now in PCB. That's a PCB wizard. It's Coco. The real McCoyers of creating PCB. They've managed to put it and solder it into a small package. Right. So it's breadboard to veroboard to PCB. So the order actually is like this. It's paper design. It's paper design. Then from paper design, you go to breadboard. Then from breadboard, you go to veroboard. Then from veroboard, you go to PCB. And then you have your final design, your package or your package. That's the order there. Now there's another 2 comments. Let's check. CAD are for designing purpose. Of course, they are for designing, for example, those circuit diagrams that I was saying yesterday, you're supposed to draw a circuit diagram. You can use a CAD package to design that circuit there. It will actually simulate. There's what is called simulation on it. You can actually simulate to check whether that circuit of yours will work or not. So the CAD software will actually tell you, no, there's an error in your circuit. And then you check what the error is, sort it out, simulate again. You will see LEDs turning on there on your software, showing that it works, buzzers buzzing, and stuff like that. So yes, on that part. And then what was the other comment there? If to check what someone said. Oh, someone said motherboard in CAD for designing properties. Yes, perfect. That was it. Now, these physical methods of circuit modeling, this is what we were talking about yesterday. You remember, I was trying to teach you how it works. So you see, this is a breadboard, right? And I told you that this at the end, these two here, they're interconnected going all the way that way. Then in here, they're connected this way, right? And those ones are arranged that way. Where there is a groove, right, there's a cutoff. Where there's a groove, there's a cutoff there. Here, where there's a groove, there's a cutoff. All right. That's what we talked about yesterday. And then this is how it looks like. You see it now. Now, this is how it looks like a breadboard when you've connected your things now. Where you've connected your LED. They're showing you an example here of your LED, your resistor, your capacitor. Here's your battery, your 10 kilo ohm resistor, your switch, which you can press on and off. This is a 555 timer, a chip. This chip is used actually to create a square wave and the triangular waves. You won't dwell too much onto this because if I start this, I don't know. It might be something else. Rather stay on the simple ones. So just these ones I told you, it's for when you're using low voltage things. That's when you use a breadboard mostly. Veropod, you can now put AC 230 volts going onwards, right? And then finally PCB can take any kind of voltage, whether it's high voltage or low voltage. All right. And then to finalize now on these notes on our book now, there's what is called environmental and social issues, right? So every time, whether you're a clothes designer, or you're a cooking restaurant, you're a teacher, whatever profession that you're doing, there are environmental and social impact issues that you're supposed to take care of. So when developing a product, the designer must consider not only the function of the product, but also broader environmental and social issues. So this is more similar to what we're talking about, the rules of a lab. So environmental and social impact, you have to make products, making product using resources, including materials, using blah, blah, blah. The most important thing is that you must be aware of the social environmental laws. You must not litter around, do trash or have biodegradable waste or have nuclear energy around, all those things. You must take care of the environment. So be aware of the laws and also be considerate of the other people who will be here when you are now fossil fuel. You know everyone is going to be fossil fuel at a certain point. You're going to die, rot until you turn into charcoal and turn into oil of fossil fuel. I don't know, that will be million years later. So you must be considerate for the upcoming youth on that. That's what they are trying to say. Must also be aware of the social issues, the social impact of your stuff. Right. So here there's nothing much to dwell on. It's just self-studying on your own. You have to read byproducts, renewable energy sources. This is self-study on your own, design for maintenance, hazardous. That's the disposal that we're talking about. How you dispose your stuff. So disposal is very important. That's why sometimes people don't like buses with toilets, because when they flush some of those buses, no wonder they encourage you not to do number 2 in the buses. They say, no, don't do number 2. The reason is because that toilet in the bus, when you flush, that pee which is mixed in the water goes on the road. there are quite a few, maybe 1 or 2 buses who will have a sewage tank in there. But most of them, it's like a train. You pee, it goes on the railway line, directly on the floor. So no wonder they say disposal is very important. And for example, when you take ships, cruise ships, for example, there is a law that says they must dump all their waste something like 15 kilometers before the harbor, inside the ocean there. That's where they dump in. That's one of the laws. But you have to, some of these things kill fish. Nowadays, we can't go even to swim in the beach here at the Sun Coast ETC. It's all now full of nonsense there. You see now what human beings do. We're not aware, self-aware. So you see, as a designer, you need to run away from such things. Because right now, when it's a sunny day, some of us would like to go and bask there and enjoy ourselves in the water now. But we can't. There's E. coli bacteria because some people decided to dump on the harbor there, or on the coastal, thereby giving us diseases and killing fish and all of that. So they biodegradable stuff, recycling, etc. That's on your own. I can't teach you that. You're gonna have to read on your own. That doesn't. Whenever we are attacking me on the group saying I don't know English, so you're gonna have to read the English on your own on this one and understand what this is all about. And then those notes will be out. But now, before I come to a very important topic, which will be the last topic, the last and longest topic that we're gonna do, are there any questions, comrades, so far? Comrades, are you over? Before I go to one of the most hardest and painful stuff. Sarah Podcast is saying, guys, you are good. So if the comrades are good, I can hammer on. All right, now, ladies and gentlemen, what I'm gonna say is I'm gonna give you an advice about next week. So for this week, I'll stop here. But for next week, I'll give you an advice. Do not be late on Monday, Tuesday, Wednesday, on Thursday for the lecture, because I will not remind you about it. I'm time pressed on that one, so I'll be hammering. The topic that we're gonna be doing now is digital electronics. That's the hardest of the hardest topics here. So if you miss out on the first day, you're a dead man for the entire topic. And when I say you are a dead man, trust me, even YouTube won't help you on that one. So on Monday, make sure you are on time, because once I start and you're not there and I go on alone, you're a dead man. It's hard, the topic. So we're going to go to digital electronics. That's where we're going to do binary numbers, logic of 1 and 0. From binary numbers, we're going to move on to Boolean algebra. From Boolean algebra, we're going to go on again to logical functions. Then logical functions, we're going to go on again to how the vending machine works, specifically using binary numbers. So if you lose the first thing, the other thing is going to kill you. So Monday, make sure that you are there so that you do not lose all of this. So test 2, my friend, it won't be writing where we ended test 1. So everything that we studied after test 1 will be on test 2. So test 2, I won't make you write everything. You will be writing about the topics that we covered after. Those that were not covered in test 1 will be covered in test 2. And then, as you are asking, the major test or exam will consist of everything that we've learned so far. So on the exam, you can expect everything like the prac stuff, design stuff that we're learning today, information, everything. The exam. There is an example of an exam on Learn. So the structure of that exam is the same structure that you're gonna get. The structure doesn't change. What changes are the questions. So, ladies and gentlemen, I hope you're gonna have a wonderful weekend and enjoy yourselves out there. Those who have questions can ask, but otherwise for today, I thank you for your patience and availing yourselves. If there are no questions, you can have a wonderful weekend and enjoy yourselves.
Thank you.
All right.
No, sir, I wanted to add there,
Yes.
when you are saying that the session that we are going to cover is from next week is going to be hard, I wanted to add a comment there that I'll say we are really happy because you are going to make it easy for us, like you're going to make us understand. So I think since we have you as our lecturer, you're going to make things easier, you're going to explain, and I think it won't be that hard if you are going to do justice also on our side.
Don't worry, my friend. We're a family. Like I said we should enjoy, right? So I can see you are marinating me. I will also marinate you and make sure you understand. No
Thank you so
stress.
much, sir. Please marinate us.
All right. As long as you are marinating me, the family works like that. And you know that. You treat everyone in the family nicely. On your birthday, my friend, you will die of presents. So it's like that. You are marinating me. I will return the favor. Don't worry. Right. Otherwise, I can see the comrades are fine now. So, all right. Bye bye, guys. Cheers.
Bye-bye, sir. Have a
go.
marvelous weekend.
Obvious, obvious.